All right, so this is part 2 of my lecture on the particle in a box. Last lecture, we got through the point of setting up the problem, making a diagram, putting together the Schrodinger equation based on what we knew about the system, based on the coordinate system, the expressions for kinetic energy and potential energy for the system. And then we ended up with a second order differential equation, which we solved. It's an eigenvalue type equation. And we got energy levels and wave functions. And so the energy levels, of course, correspond to the energy of a particle in a state of a given wave function. So now let's look at the other sort of half of this problem, which is the wave functions. And you may recall the Born interpretation of the wave function is that the modulus squared of the wave function is the probability density. So it's giving you some idea where the particle is, where it's most likely to be found. And so looking at our expression for the various states, the n equals 1 state, n equals 2, and so on, they're going to be composed of sine functions. And so our psi n is, it's proportional to, we haven't quite normalized it yet, so we'll include a normalization constant, which we haven't defined yet. And we have sine n pi x over a, where a is the length of the box. And so if we set n equals 1, then we're going to be looking at the sine of basically from x equals 0 to x equals a. So sine we would be looking at sine over the range of 0 to pi. And since 2 pi is a full wave, including the positive going parts and the negative going parts, so we're looking at a half wave here. So we're looking at one lobe of a two-lobed full wave. And so it's going to look like this. It's going to be a function like I've sketched here that it's going to look a little bit like this. And it's useful to indicate a few things, what it is you're sketching, what the length range from x equals 0 to x equals a. And of course, one thing we have to remember, we previously defined that our wave function vanishes outside the box. So even though sine is defined for any value of x, our wave function is only non-zero between the range x equals 0 and x equals a. Okay, so we have to remember that. We can't sort of forget that and decide, well, now we're in sine land, and let's forget about the fact that our wave function is supposed to vanish at the edges of the box. That's, we don't have the luxury of doing that. So moving on to the next issue. So that's for n equals 1. Again, that's the lowest energy state. We call that the n equals 1 state. N would be our quantum number, and it's an integer starting at 1. Now, for other systems, the quantum number could start at 0. It kind of depends on how the math works out for that particular system. And so that's a wrinkle that we'll have to deal with. In math and physics, there's always a little bit of strangeness. You have to pay attention. If you just kind of forget about what's going on, you can sort of lose your way. So that's n equals 1. Now let's take a look at n equals 2. N equals 2 would that would be a function that's sine over the range of 0 to 2 pi. So that's going to be a full wave. It's going to have a positive lobe and a negative lobe. And so it's going to, there's going to be a positive lobe that's roughly at the first half of the box, and then a negative lobe for the second half. And so this looks a little different than our first state. Our first state, it looks like the most probable place for the particle to be would be right smack dab in the middle of the box. Whereas for n equals 2, there's actually no probability density right in the middle of the box, which raises the sort of, which could seem strange, because how could there be probability density on either side of the midpoint of the box? How does probability sort of get from one side to the other and go through 0? And I guess the answer is, well, it's a wave. It's not going to probably trying to think too hard of acting like a classical particle is just going to get you into trouble at that point. So yeah, there is this strange issue of there's probability on either side of the midpoint, but no probability density right at the midpoint of our box. And of course, n equals 3. Is going to have 3 lobes. And so it's going to have zeros at roughly 1/3, or at exactly 1/3 of the way into the box, and 2/3. And it's going to look something like this. These aren't perfect sketches, but I think you get the idea. One thing to keep in mind, sines and cosines are very symmetric functions. Like if we look at this n equals 1 state, the wave function or the sine function for the second half of the wave is going to be a mirror image of the wave function from the first half of the wave. Similarly, for the n equals 2, the first half of the wave here is going to look like the second half of the wave, but a mirror image and with the sign flipped in the middle. So something to think about, because we'll be looking at integrals, and so the shapes of these curves are going to be important. And of course, there's something a little bit off with my sketch here in that I set the box to be a little bit different size for n equals 3, but I think you get the idea. They're all supposed to be the same size. Now let's move to another issue, which is normalization. So our wave function is a sine n pi x over a. And then the question is, what is a there? What is the big A? What's our normalization constant? And you may recall that our normalization condition is that 1 is equal to the integral of psi star psi d tau over all space. So let's start off with that and come up with an expression. So we're going to start with 1 equals, we'll plug in our value of our wave function. That's going to be a sine n pi x over a times a sine n pi x over a. Now you may be wondering, you said that this should be a, let's see, that the wave function has to be a complex conjugate. And that's true, except our wave function seems to be real valued at this point. And you remember the complex conjugate of a real valued function is that function. Right? It's sometimes that throws students, but it's fairly straightforward if you think about it for a minute. Okay. Now, one thing that could be complex, the A could be complex, but we'll go ahead and the big A, the normalization constant, we'll go ahead and just sort of assume that it's real, and hopefully it'll work out, and if not, we'll go and fix it. So we'll start by assuming that that's real, and so we're going to first we'll have 1 equals, and put the a squareds out front, and then the integral. Okay, I haven't really talked about what all space is yet. We'll just square that, and then we've got dx actually is our d tau, and then we have to stop and consider carefully what all space means. Now, we have to define all space consistent with our original diagram and consistent with our definition of the wave function. So we've defined our wave function as not existing outside of the range of x equals 0 to a. Therefore, that is all of the space that this wave function sort of experiences, right? So then it's consistent with our definition of the wave function as vanishing and being 0 outside that range. We have to set all space has to range from x equals 0 to x equals a. Okay, and that's an important and subtle point. The other thing is, if you think about it for a second, we can't be looking at a definite integral of sine squared from minus infinity to infinity, because I think we all know what the answer of that is. The answer would be infinity, and then you can't normalize, right? You can't normalize something that's a function that's going to infinity. And now, if you're looking for an excuse to stop, then I guess that would be a good one. But let's be resilient here and realize that x ranges from 0 to a, and therefore we end up with something that's going to be finite, and we can actually normalize. Okay, so then we end up with that integral. Now it turns out that the integral of this integral here integrates to a over 2. So we can take this function, and let's say first we can try for n equals 1. So it'd be sine pi x over a. Plug it into a, we can either use a computer algebra software, or look at integral tables involving powers of sines and cosines and definite integrals over certain ranges, and we'll find that maybe with a little bit of a change of variables or a little bit of algebra, you end up with this answer a over 2. Or you can feed it to a computer algebra software, and it's going to give you a over 2 for n equals 1 and for any other integer value of n. besides n equals 0, of course. So then we get 1 equals big A squared times A over 2. Or what we're trying to do is find out what this normalization constant is. So let's rearrange. That's supposed to be a 1 there. So A is equal to the square root of 2 over little a, where little a is the size of the box. So therefore, our normalized wave function for all values of the quantum number n is square root of 2 over a sine n pi x over a, where again, we never want to be, we always want to keep in mind what that little a means. It's the size of our box. And it's also good to keep in mind what the wave functions look like. It's these various waves that I've shown there. Now that we normalize the wave function, let's take a look at orthogonality. Now, we have these different end states. They seem to have different energy levels associated with them. Maybe they're real states. Let's look at this related issue of whether or not these wave functions are orthogonal to each other. Okay, we'll look at two of them, and this, of course, can be done for any number of these. Now, you can plug the actual forms of the wave function in to computer algebra software or use integral tables, that sort of thing, and you'll get an answer. But it's also good to look at this from a graphically and in terms of sort of the symmetry and properties of the functions that are involved. So don't think of sine as just sort of some function. Think of it as actually having a particular shape. And of course, shapes of wave functions end up being very important as we move further in quantum mechanics. The shapes of S and P atomic orbitals are really important in describing the various properties of molecular bonds. So with that in mind, let's take a look at our orthogonality condition and the effect of wave function shape. So what we're trying to look at is, are they orthogonal? And you remember the orthogonality condition in this case would be all space would be from 0 to a, and we expect this integral to vanish. Psi 1 star, psi 2 dx. And let's take a look at that. So we can look at this sort of graphically. We know that psi 1 is a function that looks like this. Psi 2 is going to be a function that looks like this. Okay, and then we're looking at the product of those two functions. And if you think about the way a product of a function works, and of course this is a little bit lopsided, but I think you realize that the underlying functions are very symmetric. The first lobe of psi 2 is going to look very similar to the second lobe, just with the signs reversed. Okay, so we look at these wave functions, and if we consider what is the product of these wave functions is going to be such that wherever both of the functions are positive, the product is going to be positive. wherever either of the functions is 0, the product is going to be 0, and the product of a positive and a negative function is going to be negative, right? And the product of a negative and a negative function would be positive. Okay, so with that in mind, the product of these is going to look very similar to psi2. Since psi1 is sort of positive everywhere except the edges, and psi2 is also 0 at the edges, the product is going to look, it's going to be a little bit skewed, but it's basically going to look very similar to psi2 in the overall sort of shape. The magnitude is going to be a little different, but the overall sort of shape of the wave is going to be similar. And if you look at this, let's think about this integral graphically. We're going to be, an integral, of course, is the area under the curve. Now, because of the underlying symmetry of these functions, the area under that first half of the curve is going to be equal to the area under the second half of the curve, but the second half of the curve is negative, right? It's sort of a negative area. It dips below the psi equals 0 line. And so then the lobes cancel. And so graphically, we could say this looks like the integral that the integral is equal to 0. And so we've essentially made a symmetry argument. This is our first symmetry argument. And in fact, we can sort of extend this. So by symmetry, it looks like this integral goes to 0. Similarly, we can make a related argument that all products of sort of odd-numbered wave functions and even-numbered wave functions will give a 0 integral, because you'll have some negative lobes and some positive lobes, and they'll cancel out. And or we can try several examples and integrate them out numerically or analytically, and we'll see that the integrals go to 0. Or in the numerical case, of course, it depends on the sort of accuracy of the numerical integration, but we expect it to be a very small number, much smaller than 1. So so therefore, we can either establish using a computer and also by symmetry arguments, or by actual symbolic integration by hand. We can show that psi1 and psi2 are orthogonal, and similarly psi2 and psi3, psi3 and psi4, and also psi1 and psi3, we have an orthonormal set. And we also actually expect this to form an orthonormal set because of the fact that these are eigenfunctions of the Hamiltonian operator. And we already know that eigenfunctions of an operator that give real values and where the values are different from one another, in other words, we're getting different energies for each state, it turns out that then, if that's true, then all of those states, all of those wave functions have to be orthogonal to each other. Okay, so now that we have a normalized wave function, and that's important, once we have a normalized wave function, we can calculate expectation values. And expectation values are going to tell us where is our particle on average, how spread out is it in position, And similarly, what's the average momentum and how spread out is momentum for this particle? So those are the only observables that we're really worried about so far. We'll introduce other observables later as we move on to more complicated systems that have more properties. So we're interested in things like x, expectation value, the expected average value of position, and we're also interested in the variance or standard deviation associated with position. It tells you sort of how spread out the particle is in position. And similarly, we're interested in the average momentum and the variance or standard deviation in the momentum. Okay, and this will help us to sort of flesh out a picture. It's sort of like you're trying to get a picture of what something looks like, and there are a lot of properties. There's sort of what is the color of the object, how tall is it, how wide is it, and so these, once you know more and more properties of the system, then you can say you know the system, or you can maybe make some predictions about how it's going to behave. Okay, so let's look at these expectation values or expected average values. For position and momentum. And you may recall momentum is related to velocity, right? So we're talking about motion. So the expectation value, you may recall, the general expression is if you have some operator A, some general operator, you make this sort of operator sandwich, and you're interested in you have some state psi, right? So operator has to be, can only be, the operator expectation value can only be defined for a particular operator and a particular state. Okay, so we have to define the state. So in this case, we're looking at psi and some generic state psi. And we make this sort of operator sandwich where we place the operator between the wave function and its complex conjugate, and then you act the operator on the wave function to the right. Now that's only relevant if it's a differential operator. If it's just a position operator, then acting on the right is not a important concern. And then we integrate over all space, and that gives us our expected average value denoted by angle brackets. And of course, one of the reasons why we use angle brackets for expectation value instead of just using a bar over the top is that we're also interested in expectation values of squares of operators, because those are related to the variance or standard deviation, and so putting a bar over x squared or something is going to be ambiguous. So that's one of the reasons why we use this angle bracket notation. There are some other reasons as well. Okay, so without further ado, let's go ahead and set this up. Let's first look at position. We're going to end up with an integral. It's going to go from 0 to a, because again, our wave function doesn't have value outside this range. And then we're going to have sine, and we're going to look for n equals 1. So that's going to give us pi x over a times x. And we're going to have two of these sine pi x over a. And there's the normalization constant out front, which is square root of 2 over a, but there's two of them. So we square it, so that will get rid of the square root, and we end up with 2 over little a times the integral times this integral. So this is, we can rearrange a little bit. And let's put our dx's in. Okay. And this we can solve with integral tables, and you get the answer. Well, I'll say what the answer is in just a minute. We can also think about this graphically and what this is related to. So if you have x times some function of x, and you have an integral over that whole x times a function of x, that integral is going to give you the centroid, or center of mass. And indeed, there's a deep relationship between the expectation value and the centroid of the probability density. And so, and then the question is, we know what this function looks like. We know what sine pi x over a looks like, and the square of it's going to look somewhat similar. And it's a very symmetric function. The peak in the probability density is going to be in the middle of the box. And the center of mass of that, if you were sort of sliding a fulcrum around and trying to balance, where the center of mass is, so that the masses on either side of the fulcrum cancel, it would be right in the middle of the box. So we expect that overall this integral, when you multiply it by that normalization constant that's out front, is going to give you a over 2, a over 2. Now let's start, that's halfway, or that's the midpoint of our box, which is what we expect, right? So it's always good to pause and say, does this answer make sense, right? So with math, at least somebody with my sort of middling calculus and algebra skills, sometimes I drop a sign or forget a pi or something like that. And so if I end up with something that doesn't make sense, then that usually points to some sort of error somewhere along the way. I dropped something, forgot to square my signs, or, well, that actually wouldn't change things for this problem. But so it's good to think about what do we expect to see, and then if we get something different, is that result way outside the realm of possibilities? If so, it points, if you do enough of these sort of consistency checks as you go, you can quickly find out where the problem is, and that's an important skill, because this is a fairly simple problem. As things get a little bit more complicated, we will need to be more careful and have more consistency checks. Okay, so so far so good. So it's roughly where we expect it to be, and it turns out you can do that for n equals 1, you can do that for n equals 2, n equals 3. The average position is going to be right in the middle of the box. And so we also want to look at how spread out is the wave function. How can we attach something like a standard deviation or something to its position? And what we're looking at is sort of what is the uncertainty associated with the variability from sort of measurement to measurement, or from system to system, where the systems are prepared identically but measured separately. What we're not really trying to do is trying to characterize the precision of our instrument for finding the position. We're trying to look at the intrinsic, inherent variability associated with having the particle described by this probability distribution. Okay, so moving along, so that means we want to measure the sigma squared x, which is going to be x squared minus x, the expectation value of x squared. So we already have the expectation value of x. We can square that. That will give us the second term here. Now let's first look at this at x squared. We've got to calculate that one. In order to do that, we're going to have essentially the same integral from 0 to a, but it's going to have and we'll have a 2 over a out front, and we're going to have an x squared, right, because that's the operator, is the x squared operator, and the x squared operator is just x squared times the function. Okay, and it turns out the result for this I'm not going to show because it's a little messy, and so for the sake of clarity and brevity, I'm not going to look at this. I'm going to look actually at a related issue, which is where I can use a little bit of logic and a little bit of kind of graphical thinking to get at what the answer is. Let's look at the n equals infinity case. So n equals infinity, you can think of the wave function as having an infinite number of nodes where the wave function passes through 0. So it's got an infinite number of waves packed into that space between x equals 0 and x equals a. So graphically, it's going to look, like just this infinite number of waves. Now, if we sort of blur our eyes for a second, or just sort of squint at this a little bit, it looks kind of like the probability density is constant over this range. And so if we assume, if we look at the simpler case, for psi equals a constant, that might be easier to handle. First, we'd have to normalize our wave function. So integrating, we get a squared x, iterating from 0 to a, so that's going to be 1 equals a squared a, where little a is the size of the box. So our normalization constant is 1 over square root of little a. So our wave function, 1 over square root of little a. Now that one's easier to integrate. Right, we're just going to get 1 over little a, and then just x squared from 0 to a dx. And that's going to give us 1 over a times x cubed over 3, evaluated at 0 and a. It's going to give us a cubed over 3a, which is a squared over 3. Now that's interesting. So that's a nice simple expression. And this is for the, not for the n equals 1 state, but for the somewhat similar states, kind of the limiting case of we expect actually n equals 1 to be not quite as spread out at this as this. This is sort of the limiting case of how spread out the wave function can be. Okay, and but we're not looking at the, oh, and this is of course x squared. So our let's see, so for this one we got a squared over 3, and then for the other one we got the expectation value of x is a over 2, and so if we square that, that's going to be a squared over 4. A squared over 4, and let's see, one third is larger than 1/4, right? So this is going to give us a positive value. That's another thing, yeah. We expect variance to always be 0 or a positive value. If you're getting a negative value, that means there's a mistake somewhere. Okay, so that's another consistency check. And the difference, of course, is then the reason why I liked making this substitution. I get a squared over 12 as the spread. And let's see, square root of 12, that's, so it's going to be roughly, standard deviation is, roughly a third or so times the size of the box, which sounds about right. You wouldn't expect to have the uncertainty in the position to be 5 times the size of the box. That wouldn't make sense with my physical picture. I can't see how I could arrange the particle density in such a way to do that. And it's not, 1,000 times smaller than the size of a particle, so which I wouldn't expect based on the shape of the sine function. So yeah, so this seems, like a reasonable result. And again, this is the limit as n goes to infinity. The actual value for the n equals 1 state, it's going to be close to this. It's going to be actually a little bit smaller uncertainty. This is the limiting case. This is the maximum sort of uncertainty in position for the particle in a box. So it's going to be a little bit smaller than that, and it's going to be similar. And so we solved a slightly simpler problem. We expect the actual n equals 1 case is going to be similar, but a little bit smaller uncertainty, and we can verify that on a calculator and looking at the going through the integral. Okay, so now we're only partway through. We've only looked at position. Okay, so we've normalized, we looked at position. Next, we'll look at the expectation value for momentum and the spread in momentum, and that will be the next lecture.